Good afternoon, everyone. Welcome to the 2025 Korean Academy of Actuarial Science seminar titled AI and Deep Learning Approaches in Modern Insurance and Financial Risk Modeling. We are pleased to have a series of insightful presentations from distinguished researchers who are exploring the frontiers of actuarial science and AI-driven analytics. Let me briefly introduce today's schedule. First speaker is Professor Choi from Hanyang University and myself, who will present a study titled Comparison and Predictive Modeling of Financial Behavior between Individuals with a History of Insurance Fraud and General Customers using KCIS AI training data. Second, Professor Jae-yoon An of Ewha Women's University will share research on interpretable generalized coefficient models integrating deep neural networks within a state space framework for insurance credibility. The last one is Professor Lim from the Chinese University of Hong Kong, who will present on valuation of variable annuity portfolios using finite and infinite width neural networks. We will conclude with a discussion session after 3 presentations. Thank you all for joining us through YouTube, and we look forward to a stimulating and productive seminar. 첫 번째 발표는 제가 발표하게 됩니다. 한양대학교 최영호입니다. 주제는 Comparison and Predictive Modeling of Financial Behavior between Individuals with a History of Fraud, Insurance Fraud, and General Customers using KCIS AI Training Data입니다. 자, 첫 번째 발표 시작하도록 하겠습니다. Good afternoon, everyone. Thank you for having me. My name is Yang-ho Choi, and this presentation is based on joint work with Deok-ju Yoon and Hyun-woo Shim. Today, I will be presenting our research on comparing financial behaviors between individuals with a history of insurance fraud and general customers using AI training data provided by the Korea Credit Information Services, or KCIS. Our objective was not just comparison, but also the construction of predictive models to identify potential fraudsters more effectively. So let's look at the contents. There are 6 portions. The first one is introduction. So I will introduce why we have to research this kind of project. And then next, I will describe the data set and the pre-processing techniques we use. Then next, I will describe I will move into the core methodology, which include both regressional analysis and random forest modeling. Finally, I will summarize the key conclusions and discuss future research directions and limitation as well. So let's look at the first portion. You can see the table. This is coming from FSS, Financial Services, Financial Supervisory Services in 2023. So insurance fraud is a critical issue. It is not only reduces insurance profits, but also leads to increased premiums for honest customers and promotes moral hazard. And eventually, it can collapse the financial systems too. According to the Financial Supervisory Services in 2023, the total value of detected insurance fraud in Korea exceed 1.1 trillion Korean won. This shows the seriousness and growing scale of the problem. I think there are several reasons why this is still growing, and then the number of frauds are increasing. One of the reasons is the legal system in this country seems to be lenient to the fraud. That's one of the reasons I believe. Okay. Then the types of fraud, you have to look at the major types. So the most of them are coming from the fabricated accident contents. It's more than 60%, around 60% of it. And then fake accidents are around 19%, and then intentional accidents are 14.3%. The main reason why we have fabricated accident content, because there is some accident, but there is no strong evidence, then they can make some stories. That's the main reason. The fabricated accident contents are the most in the types. And also the demographic trends, you can see it. There are the rising segments in fraud cases. Automobile fraud increased by 16.4%. We also see notable increases among individuals in their 30s and 40s. This is quite interesting because that kind of fraud is, you realize it, yeah, the age and 30 and 40s are mostly, they just earn more money, so they do not involve such fraud, but interestingly, that portion is getting increased. And also these demographic patterns suggest that the fraud is not confined to a narrow population segment. So, and also you see that the unemployment is 26%. So that might be understandable, but the office workers also around the 18.6% is quite a lot. Those are coming from the 2023 the FSS press. Okay, and then let's see. So the question, so we can think about that. So there are 4 of it. The one of them is empirically compare the financial behavior of fraudster versus non-fraudsters. And the second one should be, do fraudsters exhibit specific behavior patterns? So you have to notice what factor affect the most. Can we predict fraudsters based on the financial behavior? That's the third one. And finally, how can this inform institutional risk management? So those questions we might try to answer based on that data set. Oh, maybe, yeah. I just jumped to the one of the slides, so that's managed, it's a little bit complicated, but yeah, this is kind of the objective at the goal, and then we have to ask such question, then we're gonna answer it based on that data set. And the previous work, you can see it. Still, machine learning is also using to detect fraud. It's written in 2023. And then the several other papers also use some rent-car history. Then they can see the claim history about the rent-car. That's 2022. But yeah, this study focused on the financial transaction data from KCIS. So we know that in America, they use credit score to determine the car insurance premium, because the credit score is bad, then they are more accident, and that is kind of a relation. So they use credit score to determine the premium. But ours, we do not use that kind of the credit score. So we are wondering how many. So someone who is in trouble financially, then they are involved in such fraud or not. So that's managed, and we start with such data. And let's look at the data description. So we use KCIS data. The sample size is 5% of all population. So that is 2 million individual we chose. So that's randomly chosen from the data set. Actually, we cannot do. We ask them to get the sample, then they provide 2 million data. The key variables are following: the loan count and amount, and credit card limits, insurance claim amount, and fraud history. But unfortunately, so originally we start with 2 million data, so which means there are huge, I mean, the data set should be good enough to evaluate such research, but we realized that only 14 individuals with history of insurance fraud. That is a just small amount of it. The main reason is there are a couple of reasons why we have only small number. You probably realize that the number of the fraud is getting increased, but we can only find 14. The main reason is we can only take it. That data is coming from the insurance company put it. This guy is insurance fraud. So this is too small. And also someone, he or she did such fraud, but they cannot recognize it. So that's the main reason we have only 14 individuals among the 2 million. So that's the main reason because data imbalance. So that's one of the reasons we use the oversampling. So we use oversampling. So oversampling we use to address class imbalance. So we can pick 150 fraudsters and then non-fraudsters. So we can make it even. Originally we start with, because there are too small of the fraudsters, so we have to use unbalanced that sample, but we just start with evenly, so 150. So we have to oversampling from the fraudsters, and then non-fraudsters are coming from the randomly chosen from the 2 million people. So we have several way to make the oversample or some undersampling. So we can use a random oversampler, or smooth is the possible way you can try. But we choose random oversampler. The main reason is we have too small data set. So that's the main reason we want to choose computational efficiency. So that's the main reason we can choose the random oversampler. And then in this technique is usually in credit score system. So they try to use IV analysis. We're gonna select which one is good one. So the information value analysis is a data exploration techniques that helps determine which columns in a data set have predictive power or influence on the value of specified dependent variable. So we have to look for which dependent variable is working well. So this kind of the index helps you to helps to understand that kind of trend. So high predictive value variables are following. So there are 4 of it. One of them is loan amount from non-bank lenders. This is 0.88. So we see that the IV analysis, we can find it that's around 0 to 1. If the IV number is more than 0.6, we can say this is good random variable, good dependent variable. And the second one is the credit card cash advance limits. And then the third one is the number of credit card, yes. And then the last one is number of credit card held. And then a third one is credit card limit. So those will be the possible good independent variables. And afterward, because we see that the sum of the data is the discrete random variable, which is someone who makes some insurance fraud or not. This is 0 and 1. Those are the discrete random variable. But the previous one, you see that those will be the amount of the from non-bank lenders or such things is continuous. So this kind of classing means we can just separate the we can use the bins. So there are 2 of it. One of them is fine classing and the second one is coarse classing. So the major difference between 2 will be, you have to think about the strainer. So it's fine, then you put something in there, then you realize it, because that is too fine, then the most information is, it's on the strainer. So this is too much. But sometimes the coarse classing means it's too wide, so the old information is gone. So we have to choose either choose the coarse or fine classing, and then we have to pick up the suitable interval. But we realized that we did both of it, but we can find the interval is same. The main reason is we choose only 300 data total. So we use 300 data total, fine classing or the coarse classing, not much difference. But if you handle with too many data, sometimes we use fine classing and coarse classing together, then we can find the suitable intervals. So the fine classing is, yes, you can see that more than 20 bins, so we can separate too much. So we use the explore variable target relation before the modeling, and then it helps handle outliers and then missing values and improve regression stability. So those will be the good one for the fine classing. And then finally, the enables univariate analysis to identify meaningful candidate variables. So this is the good way for using fine classing. And the second is coarse classing. So this, you can see that the bins are less than 6, so which means we do not separate, too many. So we can use coarse classing, then it reduces the number of bins to less than 6 for stability and interpretability. So we choose coarse classing. So those will be the kind of merit. You can see that. Let's jump to the several examples. So let me just interpret those meaning. Yes, this is written in Korea, so it's hard to understand it, and also the number is too small. So let me just introduce this. This dependent variable is total loan amount from non-bank lenders. So you can see that should be continuous random variable, but there are only 3 bins. So from negative infinity to 770, so which means they do not borrow any money, or just up to 770, or 770 to 2800, or 2800 to the infinite, so which means that there is no cap. So they separate 3 categories, 3 bins, and then those means this blue means non-fraudster, and then this red means a fraudster. So this one, 243, that kind of stick represent the first bin. So 243 individuals belongs to the debt bin, and only 35 belongs to the second bin, and then 22 belongs to the third bin. And then this red represent among the 243, those guys are fraudsters. So you can see that this 81% represent the number of the first bin. How many? 243. So the 81% belongs to that first bin, and the red one or blue represent among the 243, 42%. Here, 42% are just fraudsters, but this 97.1 represent among this bin 35 individual, but almost 97.1% are fraudsters. So which means among the second bin, most of them are fraudsters. So you can see that the major difference. You can see you separate the interval, and then each bin shows a different schemes, something like this. And the second example is also the average credit card cash advance limit. So we can see 3 possible bins, and also it's not much differ from the previous example, but you see that this one is huge because 97%, but the second one, this is randomly chosen from the computer, so we do not use the in purpose. So the computer choose the best interval for such a graph. So for the average credit card cash amount limit, then you can see among the second beans, there are 76.7% are fraudsters. So anyway, you see that the 3 beans, the first one is, you can see that half of it are fraudster or non-fraudster. So among these beans, we cannot find any difference, but you see that in the second bin, there are more fraudsters belong to here. So which means the credit cash advance limit is in 150 to 280, then they are more, they seems to be more insurance fraudster. So which means such kind of information helps to predict who belongs to the insurance fraudster or not. So those are the kind of examples you can see it from the fine classing. But I originally previously mentioned that the coarse classing or fine classing is they use the interval, so they both have the same result. And then finally, we're going to use the logistic model, regression modeling. So before we start to do that, we can try to look for the correlation between the variables. There are such variables are possible dependent one. Then we can use, we realize it as such good, using the stepwise regression. So we can choose 6 random variable possible. So those will be from the computer. So we use the logistic regression. So we try to get as such. So I don't want to go over as such and such in detail. And then this will be usually use the credit card score. So look at this. The number of insurance claims you can divide 4 bins. But we use IV. There are different bins. So because these bins are coming from the regression. So we originally start with correlation first. Then we just get rid of some strong relationship, and then we can find a little bit different bins. So in this situation, there are 4 bins, and then you can find such points, the credit card points. And then this is one of the example. The credit score is coming from the beta. This is coefficient, and then WE plus n over alpha over n times factor plus n offset over n. So from this example, we can find the first one, the 83s are coming from the number. You can pick it up, the coefficient, and then WE plus alpha over n, and the factor. So the factor is coming that way. The offset is, we use the 500 is the, what is that? This is the maximum score. You can earn it. So I just use 500, and then the factor is coming. This kind of formation is we just set it up, and then this one, that number of insurance among the bin minus infinity to 1, that is 83. So this is the result for the regression, logistic regression. So the significant predictors are those 4 random variables, and then we use KS statistics. This is 0.693. So this is a good one. So I just want to show that this KS means we can separate good people and bad people, and then we have to see that kind of the difference between those. So if the KS is more than, I heard that more than 0.4 or 0.5, then this is good one. So this regression result is fits well. And afterward, I will show kind of prediction. So we use train and test split 70 and 30. So still it's working well. The ROC, AUC looks like that way. So it is very high. So this means this model can predict well. So this is almost the end. So finally, I just want to use that we end up such conclusion. So fraudsters show distinct financial behavior. So you see that because of some financial problem, they probably think about this insurance fraud. So that I do not know what is the cause and effect, but this is one of the possible conclusion. And then second one is the predictive model I chose from the random forest shows strong performance. And the third one, logistic regression is interpretable and practical for real world use. Those will be our conclusion. But still, yeah, we have the limitation because you realize it. 7 among 2 million data, 14 among 2 million data is, yes, someone says it's impossible to analyze based on such data set. So that's one of the reasons we use oversampling, but we still wondering because if you have the better data, then we can get some the precise result at the end. So that is one of the things we can try. And also we have to think about the future plan is we can start to think about some call recording. So which means we use in Korean 면접. So we see that the insurance company only put the fraudster or non-fraudster, but you realize that there are many, but in the data set, we can only find 14 because they do not want to put those things in the data set. So we're gonna enhance the data set, so we have to use a little bit different method to get it perfect. So yeah, those will be the limitation in future work. Okay, this will be the reference. Thank you for listening my presentation. 두 번째 발표자는 이화여자대학교 안재윤 교수로 주제는 Interpretable Generalized Coefficient Models Integrating Deep Neural Networks Within a State Space Framework for Insurance Credibility로 두 번째 발표 시작하도록 하겠습니다.
Hi, today we will discuss interpretable generalized coefficient models, and this is based on joint work with my colleague Ben, who is a third speaker, and Mario from ETH. So I will start with some interesting story, and that is an interesting story for me, which give motivation of this work, and then we'll introduce our work. So let me start with Samuel Cruz story. So what are the common things you can think of from the following two pictures? So two of them looks familiar, but that is a little bit different than we know, or a little bit older than we used to think. But they are the main actors of Terminators. So here, this guy is from Terminator 1 and 2, and possibly 3. And then the other guy, which is less known in Terminator movie, but was in Terminator 4. But today I will discuss this guy anyway. But for now, let's concentrate on these two main actors. So now I will introduce Samuel Koo, who is our main actor today. So 2018, I was attending Samuel Koo's talk, which followed shortly after the remarkable success of AlphaGo. And then Samuel Koo is a professor at Harvard University. Is it? Right. So he was talking about how they have beaten Google's influenza prediction. So Google's influenza prediction was a very first big data success that we can imagine, where Google has used big data to estimate influenza prevalence in real time. So this was like a textbook example of how big data can make things work. But soon it was challenged by many other statistical groups due to some inaccuracy in their predictions. So in Google's influenza prediction, they just utilize big data without thinking too much. That data is from Google search queries to estimate the influenza prevalence. So this is big data. But what Samuel Koo did was that so this is big data which is only available for inside people from Google, not for us. But what Samuel Koo did was that he used small scale data which is available to the public and then use very simple statistical model to beat Google's models. So he demonstrated significantly improved performance compared to Google's method. Now, so while I was attending this talk, I was still on the human side. So I was very happy that Samuel Koo, our hero, human hero, has beaten the evil AI. So I was very happy. And then for the time being, he was my hero, statistical hero. Now things changed because now we have GPT and very powerful AI machines. So even very top research scholars give up to beat up those evil AIs. So they just do whatever they can do on small things. So before I talk too much about that, let me talk about Terminator 4. So in Terminator 4, the other main actor here, this guy is called Marcus. He's a cyborg. He's a fusion of human and machine. And this hybrid model symbolizes how combining human intuition and machine power to create a stronger force. So this metaphor guides our perspective on AI, not as a replacement, but as a partner. So let's coming back to real life. So now it is GPT era. So until 2020, AI system operated with minimal human involvement. So Samuel Koo's success with flu prediction reminds us that well-guided human model can outperform brute force data algorithm. But since release of ChatGPT, which is approximately 2022, when they have become popular, human input has become central to AI system. So interpretation is very important. Of course, interaction is also very important. So this marks the rise of collaborative intelligence, human and machine working in tandem. So to enable this collaboration, interpretability in machine learning or deep learning became essential. So in this talk, we explore interpretable deep learning model approach in the context of time series analysis and also focusing on insurance credibility. So let's come back to small scale prediction. So our goal in insurance is to predict insurance premium based on the historical data. So typically we have used credibility, which can be viewed as linear regression in statistics. So this is highly interpretable, but of course could provide limited accuracy if real model is not linear. So alternatively, we can think of AI machine, which we can also call black box model. So this can be very accurate, but it hardly provides intuitive interpretation. So here, what people has proposed is somewhere in between the linear regression and black box machine. So it is called generalized coefficient model. So it resembles that of linear regression, but coefficient itself becomes a complicated function of observation. So and then this linear coefficient can be constructed from neural networks. So somehow it looks like it is a hybrid between linear and complicated models. And of course, the third category that we can imagine is statistical model. So it's not a linear regression, but not a complicated machine learning, but it is traditional. It can be traditional time series. So it is powerful if the real life follows this simple rule, but we can hardly think that these some simple rules can dominate. So either way, the statistical model can be too simple to be true. So now let us provide our main model. So our goal is to use neural network and the statistical model to have generalized coefficient model. And then, so we will, from the statistical model, we will use state space model. And then we will combine this state space model with the neural network so that we will provide generalized coefficient model. So let us coming back to generalized coefficient model and why we are not satisfied. Let me explain why we are not satisfied with this model. So this is our goal, and to predict this, we can use generalized coefficient model, where this coefficient can be interpreted as a kind of dynamic coefficient, which is not a constant, but also a function of observation itself. But there should be some identifiable problem. For example, let me think of two sets of prediction. So one set is red color, the other set is blue color. So, and then it is possible that these two colors can predict the same prediction even though coefficients are not the same. For example, so this is 0.5 times y1, y2. This is 0.5 times y1, y2. So when you add them up, you will have y1 times y2. But y1 times y2 can be represented in this way and the other way. So of course, y1, y2 does not change to anything, but we can express in, for example, in two ways. So that this is one kind of dynamic coefficient model with the coefficient 0.5 y2, 0.5 y1. This is another kind of dynamic coefficient model with the coefficient y2 and 0. And then, so if you insist that they have interpretability, so you are in trouble because you have two kinds of different interpretability. So red interpretability and the blue beta interpretability. So obviously this does not give us interpretability because of they are not identifiable. In other words, interpretation is not unique. Non-uniqueness of interpretation means no interpretation. So to resolve such a non-identifiability problem, we will use time series model called state space model. But usually, state space model can be regarded as some kind of best small model for time series analysis, but usually it does not provide the closed form expression in general. So if you want to use it for predictive purpose, you can hardly think of this kind of nice closed form expression for prediction. But on the other hand, there are another type of state space model called observation driven model, which is less known and then less popular. But this kind of model can handle such issues so that it provides us closed form formula for prediction. And then, compared with parameter driven one, literature on the observation driven one is weak, and we can hardly use literature. So summary of overview is that dynamic coefficient model suffers from identifiability problem, so that it does not provide us interpretation, contrary to advertised. On the other hand, we can use state space model, which is a statistical model, so that it has more interpretability, but unfortunately, they provide non-analytical form of prediction. So our approach in the next chapters, the next remaining chapters, is to use observation-driven state space model to give closed form solution for prediction, and then we'll also show how to combine these models with the neural network to give the dynamic coefficient model. But this dynamic coefficient model implied by our model is safe from non-identifiability problem. So which means our induced dynamic coefficient model is identifiable, so that we have interpretability while using neural network. So still I said it's a review. So this is how parameter-driven state space model is organized. So we have observation, and let's say n is observation, and then this observation is governed by non-observable some characteristics. You can think of this as some kind of gene from your brain or from your body. So as time goes, your gene changes. You can think of your gene is getting, your body is getting older and older. Then from that gene can explain anything, everything. So you did this because your gene is this. So this is a parameter-driven state space model, and mathematically beautiful, but again, it does not give us closed form expression of the prediction. So you have to do some integration or some use numerical method to achieve this value. On the other hand, observation-driven state space model is not mathematically beautiful, because as you can see from the arrow, it goes from anywhere to anywhere. So it's not beautiful, but this is useful. Not beautiful, but useful, because we can use of this complex design so that we can. So complicated means it's complicated, but there are more rooms for us to do something. So we can do something so that this prediction becomes analytical or has a closed form. So this is complicated, not mathematically beautiful, but practically good, because it aims to allow the closed form expression for the prediction. Right. So here, since this is not statistical meeting or statistical society, we will not explain details of our model, but we can say that our model has the following property. And then using these models, we can construct neural network. I can say that we can construct somewhat generalized coefficient model, where these coefficients are constructed with the aid of deep learning models, so that our proposed model has interpretability as well as accuracy. So thanks for listening, and this is a reference that we have used. Thank you.
예, 지금까지 발표 잘 들었습니다. 마지막 발표는 차이니즈 유니버시티 오브 홍콩의 림 교수님께서 Valuation of Variable Annuity Portfolios Using Finite and Infinite with Neural Networks라는 주제로 발표를 진행하기로 했습니다. 자, 발표 시작하도록 하겠습니다.
Hello, my name is Ben Lim from the Chinese University of Hong Kong. So today I will be presenting on a paper which I have done with my two other co-authors, both from the University of Iowa, my advisor as well as my academic brother. And we'll be presenting on the valuation of variable annuity portfolios using finite and infinite width networks. So this will be a more methodological type of paper where we aim to mainly introduce this methodology of using the infinite width neural networks, which we will call the neurotangent kernel. So we will see as we go along with this talk. But the main point is to introduce this methodology as something that can help to use neural networks in a more simple and effective way compared to the traditional method. So I will start by introducing the neurotangent kernel regression. We'll talk about the motivation using this traditional kernel regression, and then we'll talk about the definition of what is called NTK. And we will illustrate by applying this to the variable annuity portfolio application, where we will see that the properties of this NTK allow us to do this problem quite nicely. So, as we know that most of the current advances have been done with the neural networks, especially as Professor An has mentioned on the AI and the ChatGPT, everything has been relying on the neural networks. However, if you are just someone that is, as we know that we can use ChatGPT to fit a lot of models using the more verbal prompts, but for persons that want to use machine learning a little bit more intensively and are not super experts in the neural networks, starting to learn can be quite difficult because, as we know, the neural networks requires us to tune the hyperparameters, and the correct configuration depends on each problem instance. And also, you need to know exactly how the loss works, and figuring out the optimizer and the gradient descent algorithm, and all of these things can be quite tough. So this has made it so that, for example, practitioners in actuarial science find it quite tough to adopt neural networks in their daily work. A lot of people leave it, for example, to data scientists to try to fit the neural networks. Okay, so what we plan to do is that a recent work by Jacob et al. 2018 has showed that there is a link between neural networks and kernel regression. When we take the neural networks to the limit and make it so that the number of nodes is infinity, they have shown that it converges to a kernel. And this kernel is known as the neurotangent kernel. So what our work is to show that this neurotangent kernel, which has been applied in other fields, has useful applications in actuarial science and is a useful tool for actuaries to use and pick up so that we can be more efficient in fitting the predictive models. Okay, so now we'll start by introducing this kernel regression. So kernel regression forms the basics of this neurotangent kernel, since the neurotangent kernel will be one form of kernel regression with a specific kernel. But what is kernel regression? So we start by thinking about a function that we want to predict from the data. But we know that if we are just using a standard linear model, it will not model this function well. It's very limited in flexibility. So instead of using the raw data, which is x, why don't we think about taking a transformation of x? So this transformation, usually we think about just maybe finite dimensional transformation, but it's not necessarily have to be finite dimensional. We can in fact think of infinite dimensional transformation. Okay, so that means that the transform item is no longer a vector, but actually going to be a function, something which is infinite dimensional. And so when we fit a linear model on an infinite dimensional object, we are no longer thinking about a coefficient vector, but instead we are thinking about a linear functional. Okay? So one thing it has been shown is that when we are fitting this linear functional, even though in some sense it's like an abstract coefficient, and in fact the risk representation theorem says that, yes, we can think of that coefficient as a coefficient in some sense. So we take some coefficient function, in this case, and multiply inner product with our transform function. And this representation is possible. Okay. So just a very simple example to illustrate the power of this kernel regression. We can see over here that the blue dots is on the inside, the orange dots is on the outside. If you try to use some sort of linear boundary to try to separate the orange dots from the blue dots, you are hardly going to find a correct thing to do that. But now, let's think about, let's not use the original data. Let us transform it so that we take the radius from the center. So now, when we look in the dimension of the radius from the center as the dividing line, now we can clearly see that the blue dot and the orange dot is very clearly divided by just the middle. Okay, so this shows that we want to be taking transformations of the data to be able to find the correct dividing line in this case, whereas in more general case, what we want to do is to find some transformation of the data which is able to create more predictive power than just using a linear model on the original data. Okay, so some more basics about kernel regression. When we are doing kernel regression, we have to fit an infinite dimensional coefficient, which makes it computationally infeasible. So one key to be able to use kernel regression efficiently is what is called the representer theorem. The representer theorem says that the coefficient is always of the form some linear combination of the transformed data. And this is not on just the transformed data, this is on the transformed data only on the n observations in the data set. So originally we have infinite dimensional problem, but now we only have, you can see that there is only alpha j to n, alpha 1 to n. So that means that now we only have to fit n of these coefficients. So we have transformed the infinite dimensional fitting problem to n-dimensional fitting problem, and this makes it so that we have much more feasible way to fit the actual coefficients of the kernel regression. And so in this way, we have taken the problem and transformed it to, in some sense, a new linear model problem, a new least squares problem, and you can see that in some sense, the covariate vector is just the inner product of the transform vector. Okay, so in this case, what you can see that the key here is this inner product of the psi xj with psi xi. So what we need to specify is just this thing. This transformation between the two of the vector is what we call the kernel. Okay, so this feature map, as we have seen that the psi here is in here, right? But actually we don't really need to know what is the psi. What we really need to know is just the function that comes out from taking the inner product of psi x with another psi x. And so this function is what we call the kernel. Okay? And one thing, that is another theorem, it says that as long as you have a symmetric positive definite function, Z will implicitly define some psi. That means it's a feature map that you can think about the infinite dimensional coefficient. We don't really need to know what is exactly that feature map, but we just need to know that it exists and it will create some nice properties. Okay? So now we come to the main problem in the kernel regression. In kernel regression, the main challenge is just that usually the k, the kernel function that we choose, is very, very simple. For example, just some exponential of the square of the distance of the two vector. It is very simple. And usually the choice of these very simple functions are not good enough to give high predictive power. We will see later in the application problem. So the idea is, how can we choose actually something that is good for prediction power? It turns out that the idea of this NTK will give a solution. Using neural network, we know that neural network does well. So if we use neural network to define a kernel, then we can expect also it will do well. And so that is the main idea. If we have a neural network function, if we take the width to infinity and then we just do a linear approximation around it, what we will see is that we will have an inner product around here. Okay? And so what it turns out is that as we take under certain conditions, we take this linear approximation, we take the width and we go to infinity and we normalize it appropriately. As we take the width going to infinity, then the linearization, this is supposed to be a linear approximation, right? But as we take the width to infinity, what Jacob et al. Found is that this linear approximation actually approaches and becomes actually true. That means the approximation and the actual function, the difference actually goes to 0. And so using this, actually what we can do is that now we can use this linear approximation to define a kernel. And so this kernel is what is known as the neurotangent kernel. And because this linear approximation in the infinity approaches the true value, so that means that if we fit a kernel regression using neurotangent kernel, this will be the same, equivalent to fitting a neural network with infinity number of nodes. And so this allows us to fit any infinite width neural network. Since we are fitting n-dimensional coefficient, in the very standard case, we have to do the n by n matrix inversion. But if we don't want to get the exact value and we just want to do gradient descent, then this gives order of n squared, which makes it quite feasible and useful for the fitting the kernel regression. So we have taken what is an almost infeasible problem, which is trying to fit an infinite width neural network, and we have reduced it to something which is feasible, which is now a kernel regression. And this kernel regression, because we know neural networks have good performance, we can know that this has high predictive power. Okay? And now you might ask, we are fitting infinite width neural network. Is it possible that it does well? We know that there is too many parameters. Is it working well? So one research by Belkin et al. 2019 showed that there is in fact one phenomenon called this double descent. In the traditional, we think about bias variance trade-off. So we think about, okay, too much, there will be high variance, too little, there will be high bias, and so there should be something in the middle so that we can have the balance, the best error. Okay? But it turns out that Belkin et al. Showed that a phenomenon actually happens if you increase the number of parameters more than the number of data. You see that this curve doesn't actually just keep going up, but actually it will start here and go down even further. And as you take the number of parameters to infinity, it in fact can approach 0. This is what is called the double descent. You can see that it goes down. This goes down once and twice. So that's what is known as the double descent. And so this is our justification for when we can use the infinite width neural networks. Because we are fitting something with the number of parameters which is around here, so that allows us to actually get better predictive power than something that actually just try to find the minimum bias variance trade-off, which is around here. And one research by Aurora et al. Actually tried to apply this NTK on the UCI datasets, which is a traditional benchmark, and they have shown that it outperforms the standard neural network on 50 out of the 77 datasets. So we are going to take this and try to apply it to variable annuity evaluation. So I'm going to go through this setting a little bit quickly because I want to get to the results. But the main point is that in variable annuity evaluation, we use nested Monte Carlo, which is very expensive. And so what we want to find is to find some sort of predictive model. We are going to do this thing which is known as meta-modeling. Okay, so instead of doing the very difficult computation on this very big data set, what we are going to do is that we are just going to get a very small data set. So let's say that we have 200,000 data points that we want to find the F for. So we're just going to take a small data set, let's say 1,000. We are going to use the difficult method to compute the values for this. So from here, we get a small data set. So from this small data set, then we are going to do prediction. We fit some regression model on this very small data set, and we're going to do prediction to extend the values to the big data set. And so from here, what we're going to do is to see how well is our prediction. Can our predictive model give good valuations for the rest of the data points that we don't have? And the dataset that we're going to focus on is this Gunn and Valdez 2017 dataset. Because this valuation is very time-consuming, this synthetic dataset actually has the correct values for almost 200,000 policies. And so this will basically help us to be able to evaluate the correct performance of our methodology. And this has been used in many other studies, which is trying to study the predictive power of the meta-modeling. So what we are going to do in here is that we're going to show that the current benchmark is tree-based models such as random forest and boosting. And what we're going to show is that step one, we just show that standard neural network do better in terms of the mean square error than these tree-based methods. Then in step two, we're going to show that the neurotangent kernel regression also further outperforms the standard neural networks. Okay, so for the standard neural networks, we are going to use a very simple two-layer network, and we're going to use two different versions of the network. One with just using one-hot encoding for categorical inputs, one which is using the entity embedding for the categorical inputs, and then we are going to use out of these two, we train two different networks, and we choose the one which has the smallest validation loss. Okay? We're going to use a small training portfolio, which is 680 policies, 0.735% of the whole data set, a small validation set of 340 policies, so half of the training portfolio. And we're going to use just since this is not focused on the choosing what is the portfolio, we're just going to use stratified random sampling for this purpose. Okay? And we're going to benchmark against several different methodologies. So we have a different competitor neural network methodology, which is based on Hejazi and Jackson 2016. We are going to compare with three different tree-based methods as well, bagging, boosting, and bias-corrected bagging. And we're going to compare mainly based on this mean square error metric, but we're also going to look at the different metrics as well based on the percentage base and as well as the average percentage error. So we can see this is the first display. We can see that out of the different metrics, in terms of almost every metric, we can see that the standard neural network choosing between the entity embedding and the categorical approach outperforms almost everything else from the tree-based category, and also outperforms the competitor in the Hejazi and Jackson 2016. So we can see here a very clear demonstration that neural networks is one of the useful methodology to be using in this variable annuity evaluation. Okay. Now, the question is, kernel regression. Just now we have said that kernel regression is something that is because we are using the representer theorem and we do the matrix inversion, so it is easy to use. But the question is this just using standard kernel regression without using the NTK, can it perform better than neural network? And the answer is, it can do better than the tree-based model, but it cannot do better than the standard neural network. Okay, so standard neural network, what you can see here, the disadvantage here is the time. It takes 20 minutes to run this neural network. Whereas kernel regression does well, somewhat less well, but it may be better, but the time is much less compared to the neural network. So we have kernel regression, which has okay performance, but does very well, runs very fast, easy to use. We have neural network, which does well, but at the same time difficult to use and runs very long. Is there some way that we can find something that can do both? And so that's where we introduce the neurotangent kernel. So in neurotangent kernel, really there is much less choices that we have to make, because in neurotangent kernel, all the width of the neural network is infinity. We don't have to think about, okay, 128 nodes, 64 nodes, anything like that. And also, because we are using kernel regression, we don't have to think really too much about gradient descent or anything like that. All we need to do is really fit kernel regression, and we just need to say, our neural network looks like this, and then we fit the kernel based on that. So what is the parameters that we really need to choose in this NTK regression? First is what activation function that we're going to use. ReLU is the standard activation function that we're using in usually neural networks. We'll see that in this case, it's actually not necessarily the best. And also we're using ERF and the JLU. So the activation function is somewhat limited, because to be able to have the closed form for NTK, there is only we have to take certain expectation and normal distribution function, so there is certain limitation. So either 1 or 2 hidden layers, and in the NTK, we do not have such thing called entity embedding, so there's only one hot encoding for the categorical variables. And then there is the weight variance and the bias variance, which we will be tuning. Okay. In this first part, let's just first tune this weight variance between 0.1 to 15, and we'll set the bias variance at some small value, which is recommended as the best practice in the literature. Okay, so what we can see by just doing this tuning of the weight variance is that there's usually a beginning part which is very noisy, but very quickly you can see that it's going down, and then there is some thing in the middle here. In some sense, hyperparameter tuning is something like a choosing where is the minimum validation error. And what we can see is that in general, the validation error, which is given in blue, and the test error, which is given in red, usually have very similar points where the sigma W is minimum. Okay? So by doing this, now let us look at the performance of the NTK. So let's just again focus on the best performer from each category. Previously, we have the neural network being the best performing. But now, moving to the NTK, we can see that the best performer in each category actually can have much better performance compared to the neural network. Okay? And further, what we can see is the time. The time which is coming out of the NTK is much less compared to this 20 minutes. In the NTK, it takes less than around 10 seconds just to fit the model. And we have shown previously that the hyperparameter is also quite easy to tune compared to the neural network. In the neural network, to be able to tune the hyperparameter, I have to run this thing 20 minutes each time. Whereas here, I can only run 10 seconds each time and can choose the hyperparameter quite quickly. So what we see over here is that usually in our conventional neural network, we think that 2-layer network is better than 1-layer network. But in this case, actually that is not necessarily true. we have one-layer network actually maybe a little bit better than two-layer network, and also in terms of the timing, it takes less. So why is this possibly? It may be because we are thinking about no longer just the finite width neural network, but actually infinite width neural network. And so we are no longer limited to just having to use the two-layer to be able to get good predictive performance. With the infinite width network, it is possible that one layer is actually enough. Okay? So we can see over here that by doing this, we can combine the advantage of this kernel regression. We have said that the kernel regression, the advantage is easy to use. By moving to this NTK, we now have easy to use as well as the good performance and possibly even better performance than the standard neural network. Okay? So, of course, we have shown here that we are doing actually very simple levels of tuning. Okay? We can, of course, do better than this. But before that, let me just move forward with another application of this variable annuity validation. In the actual application, what is of interest is actually the prediction of the first order derivative or the Greeks of the variable annuity valuation. This is used for the hedging. The company want to be able to know exactly what type of the portfolio they want to hold to be able to hedge the portfolio most effectively. So to be able to do that, they need to figure out what is those first order derivatives. And so meta-modeling is used to first step to get the delta on the first small portion of the data set, then use the meta-model to predict deltas on the remainder of the portfolio. The goal of this exercise is to be able to get the deltas correct down to very small percentage error. So we're not concerned with the mean square error, but more with the percentage error on the whole delta. And we can see that here we are doing the 5 replicates, and we can see that in most of the cases, the NTK does pretty well in terms of it's not all the time the best, but we can see that in general, it has very consistent performance of being very low percentage error compared to the other 3 methods that we have considered here. Okay. So the last thing I want to present is just about the further tuning of the parameters. So just now we have just talked about the very simple, okay, using just the sigma w as a tuning parameter, but we have not talked about other further tuning. So one further tuning that we can do is actually with the with this thing which is known as the regularization parameter. So just adding a small constant, because as we know, the kernel regression is actually some sort of the linear model solution. And so if we add a regularization, just like in the ridge regression, actually we can help stabilize this a little bit more. And so what we see is that the regularization helps improve a little bit from the standard kernel regression, just using the sigma w level of tuning. And of course, we can also tune with the second parameter, which is a sigma b. And we can see that this also improves the performance a little bit. And then we can actually combine these two. So we have 1, 2, 3 parameters, sigma w, lambda, and sigma b. So this is a very big grid. So what we can do is just do a very simple coordinate descent algorithm to tune the hyperparameters with respect to all 3 of these. And we can see that the resulting gives us much better, slightly better performance even compared to just doing the regularization. Okay, so that is the, to summarize, so we can see that neural networks do well in terms of the predictive performance, but it doesn't do well in terms of being complicated to use as well as the runtime. Kernel regression does well in being easy to use, but it's not very well performing compared to neural networks. And if we use NTK, we can combine the advantages from each of these methods. And so what we have shown is that the predictive performance is better by using the NTK. And one other thing I just want to mention here is that because we are using the NTK, which is we are weighting each observation, there is some sort of interpretability because we have the weights for each of the observations. So there is more interpretability compared to the neural networks. So hopefully this talk can help you to be able to use a little bit more in terms of the NTK so that you can be able to utilize the predictive power of neural network without having to learn too much about the two details. Okay, so that's all from me. Thank you very much.
예, 지금까지 세 분의 발표자의 발표가 마쳤습니다. 이제부터 토론하는 시간입니다. 토론도 마찬가지로 영어로 진행이 될 예정입니다. 자, 지금 이제 토론을 시작하도록 할 텐데요. 바로 영어로 시작하도록 하겠습니다. So, three presenter is done. So, we are going to discuss our presentation, so each other. So, if you have any question or a related issue, let's talk it freely. So, who's gonna do first?
Okay, let me first start some question. So you are talking, Professor Che, you were talking about how to detect the fraud, insurance fraud, and then even though you have one machine, there are many thresholds that you can choose, and then if you choose too high threshold, you may encounter, as your insurer, you may encounter this problem, and then if you have too small, you may have another problem. So what is the main problem that you can think of by selecting such a threshold?
Yeah, we don't think that one not too much because we just handle it only small, 14 individual at first. So at the beginning, so it's too small. So we start to think about, is that possible you can research on that small data? At the beginning, I said no because it's too small, but we're gonna start just kind of starting because we just make some oversampling first, and then we try to see is there any specific difference is coming. That's just that's on this paper. So if you ask such question, then we can do a little bit later. I mean, yes. So that's kind of next step. So we can think about that.
Okay.
Yeah.
Okay, so Professor Che, I also have a question. The thing is that even though you're doing the oversampling, it doesn't change the fact that you only have 14 data points. That is actually fraud. And that means that each one of these just represent exactly one combination of the covariate, which has, in some sense, we can think about the 14 data point is very clearly fraud because that is the one that insurance company managed to label. That means that there are still many fraud case that is hidden in the data set, which we don't know. But what we can say is that this 14 data points is the clearly in the fraud. So how do you think that this small number of data will be a limitation to the, I guess, in the future?
At the beginning, so the KCIS use this combination because this is not only one data actually data set. So we have to use a kind of choose the number of the insurance policy, I believe, so we can combine. When we combine such, and then that's the problem because we can find only 14 individuals. So that's the major issue. So, but we cannot ask them. So you try to give me just raw data, and then we can try to combine. But they don't want to do that. So they just give us just only 2 million data, and then we try to see the combination. Then it ends up only 14 individuals. So that's the main issue probably. So if you have some kind of the way we have to manage the data, then probably you ask such things, then we have better data probably. So then I think the better result is coming. That's what I think. But it's very difficult to ask them. We have to use the manageable data. They do not give us such.
Yes. So would the KCIS be open if you ask them just for not for the whole data set, but rather just for exactly the fraud cases? Because I believe that the 14 does not represent all of the fraud cases that they have.
Yeah. So that's the issue. So when I ask them, so we want some fraud case, but they do not provide and such. So that's the main reason. Yeah. I hope. Yeah.
Yes, I hope that this research will motivate them to give you more of those.
Because this is kind of the beginning. Yes. So because there are certain differences coming, so we're gonna see the more details. So please provide some specific issue, then we can do better. But I don't know. Yeah. Okay. Thank you for asking such questions. So yeah.
So still have a question to Professor Che. And then in your analysis, data analysis, looks like financial credibility is one of the most important factor. And then, do you have some comment for this?
Because in America they determine the car insurance premium. They probably look at the credit score. So we believe someone who has the bad credit score, probably they are more do some insurance fraud. So there is certain the article they use here in America, 95% of car insurance company and 85% of house insurance company, they try to use the credit information to determine the premium. So if we use a certain the result, then probably see if the insurance company they are looking at the insured, then see the credit score, then they're gonna determine that the premium or something, then they might, what is that? Is that the selection adverse or something like that? So they or they can choose the higher premium to enter that the contract. So that might be one of the thing we try to look for. Yeah.
So it's possible that they will not accept policyholders with low credit risk because not only for the high premium, but also he may have some trouble.
Yes, that's right. So they also the article mentioned that credit score only we do not see that only. So we have to do it the whole things. So that is one of the portions. So the credit score is bad. So we have to think about it. So we cannot choose that because of that guy's insurance fraud. So or the credit score is bad. There is some certain higher possibility to get the insurance fraud. This is not true, but we have to think about that because we have to combine. This is one of the information we can determine the insurance premium. So that's one of the possibility we have to think about that. Yep. Thank you for asking. Yeah. And I have a question for the Professor Lim.
Yes.
So we have to think about always the running time and the accuracy. So we have dealt with which we have balanced those two. So the NTK process is one of the best things. So we have to reduce time. Also the accuracy is always they perform very well. So but is that possible? We have certain the insurance company has lots of data. So all of the data can. This method can be applied to anywhere in the data set.
Yes. So currently, one of the major limitation, or in fact, that the reason that we choose this meta-modeling as the application case is exactly because training data is small, and therefore that it can run in a reasonable amount of time. Now, in the case of bigger data, we are trying to, so there is the kernel regression actually requires certain more specific type of method to be able to fit onto the larger data set. Is you can remember what I mentioned in the presentation is that to figure out the kernel regression, we have to invert the n by n matrix, which is an n cube level of the operation. And right now, if you try to do that for even just slightly bigger data set, like maybe 10,000 data points, it can be take very, 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 very long. So right now, the main application case will be in this very small data set case, not in the very huge data case.
Okay. So it's just the following question is, so you just record the time only it's running on the program. So
Yes.
Is there the way you can try to find the NTK? So you have to convert that kind of the matrix.
Yes.
So how much time needed to convert the data to the n squared, the matrix?
So that is also actually included in the runtime.
In runtime. Okay. Wow.
Yes. So right now, the good thing about this NTK is that there has been a package in Python which is used to, because the NTK requires some closed form expression, which is not straightforward to implement. And this Python package actually is able to take your architecture and then it compute the necessary expression to be able to compute the NTK matrix.
Wow, it's great. I just think because it's just too small time, so I think that one, the converting time is not included. So but it's kind of package. So wow, it's great. Yeah. So it's very applicable, right, to the anywhere. Yeah, that's great.
So I have another question. So in your example of data analysis example of using it to variable annuity. So you have selected a few scenarios out of many scenarios.
Yes.
Then do you think you may have some kind of so you have lots of explanatory variable, but you only have few response or few observations.
Yes.
Then may cause some problems, right?
Yes, that is exactly the challenge of this meta-modeling problem. Is it possible to use very small data set, but at the same time get good predictive performance on such a large data set? And what we have found is that through doing a few replication, the one report is not just the only time that we run this thing. We have found that over several other replications that the results are quite consistent. That even though, so the other thing that I mentioned is also with what is known as the double descent phenomenon, right? But even though parameter is much more than the number of data, the second descent is the key.
No, but I'm not worrying about that training, validation, that kind of things. But I'm more worrying about that. So all the explanatory variables are here. I don't know. I forgot how to express it in terms of statistical term. But all the explanatory variables are here. But what if your explanatory variables exist there, like leverage or something?
Oh yes.
Then,
right. Actually, in that case, my problem is very similar to Professor Che's problem. That there is very few data points available to explain the many characteristics, right? So in that case, well, that is exactly what is called the portfolio selection problem. Actually, that is to the in this demonstration, we did not focus on the portfolio selection problem of choosing which portfolio we should focus on in the training data. that is a separate category of the literature in the meta-modeling. But it is possible, yes, to improve the training performance by choosing carefully which combination of covariate to focus on.
No, I don't want to choose that. So what if because I like to have all of them.
Yes.
So one possibility I can think of as a non-expert is that I will do this NTK several times with several new samples.
It is now exactly the constraint in the variable annuity problem is that the training data is tough.
Right.
That is unavoidable constraint in the NTK.
But you may detour those kind of problem by using least square Monte Carlo kind of mechanism, so you don't intensively calculate accurate things, but you aim to calculate fast with some poor accuracy.
That will be exactly, I guess, will be the separate category where they try to figure out how to do the functional approximation well. But in this case, we are not really focusing on that problem.
You're right. So you cannot replicate too much.
Yes.
Right.
Okay, it's kind of valuable discussion. So I have a question for the Professor An, because you finished a little bit earlier because you just show kind of introduction much, and then you have to because of time limitation, I believe. So is it just small examples so we can apply to some insurance company or the theory of some insurance? I mean, your the method, okay? So your method can be applied to the somewhere. Maybe just small example. Just tell us about that.
Right. So when we think of traditional credibility model, then it tries to predict premium based on the past data. Then traditional credibility model cannot tell the difference between the recent history and the very old history. Then we can overcome those kind of difficulty by introducing some kind of more complicated credibility where it can distinguish the seniority between claim histories, just like linear regression do. So it's almost similar to linear regression where each observation has its own coefficient. But so once again, even though this distinguish between old claim and new claims, still it is linear. So that if true model is not linear, then the accuracy can be a little bit there should be some accuracy problems. And in the case we want to use machine learning or AI, but then we may have some interpretability problem. And then looks like I'm repeating it, but our model lies in between those linear model and the complicated AI model, but taking advantage of these two, so that while providing accuracy, but providing interpretability. Sorry, I'm repeating what I have.
His model can. His model can explain the black box phenomenon, because that AI model can show the result but without interpretation, but his model can do. So that's what he wants to mention it, right? So is there any things we can discuss more?
Oh, so my last question for Professor An is that you have mentioned that the identifiability is solved by using the proposed model, but I believe you don't quite provide explanation. I mean, there is too much detail. So I don't quite catch what is there some simple explanation of why the observation-driven generalized coefficient model has identifiability, whereas
Okay.
the one doesn't?
So first of all, it's not true that he does not understand because he is one of course. And then right, it's a good question. So big advantage of our statistical. So we have two models. Our statistical model, and then we have converted to. So we combine our statistical model with the neural network to give some our final models. So let me talk about our statistical model, which is Bayesian model. So this has advantage that we have a closed form formula for the prediction. So that if we change things a little bit, then this closed form formula prediction of linear form can be transformed to complicated AI form, but explaining how to go from Bayesian model to the complicated model, but interpreter model, which is beyond my explanation power. I cannot easily explain. So maybe I'm lack of some full understanding of the model, but still cannot explain in one word or some word. Sorry. But maybe you can explain.
I also not completely sure about the identifiability issue here. So
yeah. Okay. So I think this is time to finish the discuss. Because we have still time. I'm sorry to tell. I'm sorry telling you because the presentation and discussion is conducted in English. Unfortunately, we do not give you the simultaneous translation. So I hope at the end of the semester, each presenter summarize his research in Korean. So I'll do first, and then Professor An summarize two presentation. Okay. Yeah. 자, 지금부터 한글로 조금 설명을 드리면요. 저희 세 명의 발표를 했는데 저희 같은 경우에는 신용정보원 자료 데이터를 가지고 실제적으로 보험사기 있는 사람하고 없는 사람이 어떤 금융 형태를 따르냐를 했습니다. 그래서 어떻게 나눴냐면은 실제로 보험사기 있는 사람하고 없는 사람의 그 금융 형태가 좀 많이 달랐다라는 거. 특히 어떤 거냐면은 그 금액이라든지 아니면 그러니까 외부에서 돈을 빌렸던 금액이나 이런 것들이 다른 게 나와가지고요. 그래서 실제적으로 크레딧 스코어가 실제적으로 보험 형태에 보험 사기에 어떻게 하는지를 보게 될 수 있었고요. 그리고 그 예측 모형 자체도 변별력이 상당히 좋았다는 걸 알 수 있었습니다. 근데 조금 이제 아쉬운 점은 데이터 자체가 계속 지적도 해줬지만은 너무 이제 작았다는 부분에 대한 거하고요. 그리고 좀 더 디테일한 부분이 없었기 때문에 저희가 어떻게 보면은 이 결과값을 낸 게 어떻게 보면 이런 형태로 해서 이런 결과가 나왔기 때문에 조금 더 이제 나은 데이터를 좀 받고 하면은 좀 더 나은 결과물이 나오지 않을까라는 생각이 듭니다. 그래서 이건 조금 시작이라고 보시고요. 그 다음 뒤에 나오는 연구들을 좀 기대 있게 좀 봐주시면 좋겠습니다. 네.
네. 제가 발표한 연구부터 먼저 이야기하겠습니다. 제가 발표한 연구는 이제 옛날 클래식한 크레더빌리티 모델을 어떻게 하면은 좀 더 어큐러시도 있고 그 다음에 인터프리터빌리티도 살릴 수 있을까 하는 건데, 인터프리터빌리티는 모형이 얼마만큼 눈으로 보기에 이해하기에 간단한가, 그리고 어큐러시는 얼마만큼 복잡하게 모형을 표현할 수 있는가인데요. 요거 두 개가 어떻게 보면은 되게 다른 위치에 있는 것처럼 느껴지는 게, 왜냐하면 리니어 리그레션 같은 경우에는 어큐러시가 떨어지고 인터프리터빌리티가 높은 반면 블랙박스 모델 혹은 AI 모델은 어큐러시는 엄청 있는데 인터프리터빌리티는 떨어진다고 생각되거든요. 그래서 이 두 개 모형이 마치 하나가 있으면 하나가 모자른 대척점에 있는 것처럼 대부분의 우리가 생각하는 모형이 그렇게 생겼고, 그래서 이거를 둘 다 가질 수 없는 것처럼 되어 있는데, 이거를 한번 극복해보고자 하는 시도였고, 그 극복하고자 하는 게 꼭 우리 이제 처음에 모티베이션은 꼭 보험에 맞출 필요는 없었는데, 제가 보험 전공이라서 그런지 모르겠지만 문제를 풀다 보니까 보험에서밖에는 못 쓰겠더라고요, 방법론을. 그래서 뭐 저야 크게 나쁘지 않은데, 왜냐면 처음부터 보험을 생각하고 했는데 제너럴한 방법이 있을까, 방법이라서 해봤는데 제너럴하진 않고 보험에만 딱 맞는 상황이어서, 그래서 크레더빌리티 형태를 갖추면서 어떻게 하면 더 정확하게 할 수 있을까 하는 연구였습니다. 그리고 뭐 설명드렸듯이 제가 되게 디테일하게 설명하지도 않았고, 그래서 디테일은 제 강연을 듣고는 알 수 없었는데, 하고 싶었던 거는 그냥 이제 옛날에 한 20년 전에 통계가 안 쓰였을 때 통계를 이제 보험에 프라이싱에 쓰면은 좋다라고 여러 가지 뭐 초기 연구자들이 많이 연구를 하셨었는데요. 그런 것처럼 그냥 이제 비슷한 연구가 많이 이루어져서 이제 통계뿐만 아니고 인공지능 혹은 머신러닝 같은 것들이 보험에도 쓰일 수 있는 그런 예제들이 많아져서, 그럼 이게 확실히 더 그 예측이 좋긴 하잖아요. 그래서 그런 좀 더 예측이 좋은 예측이 좋으면 뭔가 좋은 거니까 그런 세상이 열렸으면 하는 바람이고요. 그 이제 벤 교수님은 한국어를 못하시기 때문에 제가 이제 한국어로 간략하게 설명을 하면요. 그 이제 여러분 잘 아시다시피 인공지능은 이렇게 길이랑 위스, 맨날 헷갈리는데, 아무튼 그거에서 이쪽만 이렇게 이론적으로는 이렇게 엄청나게 가져갔을 때, 그러면은 이론적인 연구는 무엇이든, 그러니까 너무 길이인가 아무튼 이쪽은 크게 가져가면 이쪽은 짧아도 뭐 심지어 하나라도 된다, 뭐 그런 이론이 있거든요. 거기서 이제 영감을 얻어서 한번 그러면은 위스만 한번 엄청나게 크게 가져가 보자 했는데, 이게 이론적으로는 가능한데요. 이제 실질적으로는 위스를 엄청나게 크게 가져가야 되기 때문에 어느 만큼 크게 가져갈지도 모르고, 근데 시간도 엄청 많이 걸리는 일인데, 이제 제가 이건 같이 한 연구가 아니라서 잘 모르긴 하지만 그런 인피니티 위스를 이제 흉내낼 수 있는 방법을 제안하셔서, 그리고 그 흉내내는 게 역시 원리는 잘 모르겠지만 엄청나게 빠르고, 그다음에 정확성은 크게 잃지 않고, 그러니까 인피니티 위스를 고려할 때, 그래서 좀 뭔가 좋은 성능과 빠른 계산을 동시에 가져오는 건데, 약간의 한계는 이제 연구자께서 말씀하셨듯이 스몰 스케일 샘플에서만 좀 아직까지는 좀 작동하고요. 왜냐하면은 데이터가 늘어나면은 n 스퀘어 오더로 컴플렉서티가 좀 높아지기 때문에 아직은 작은 스케일에서 했는데, 그래서 이제 어떻게 보면 보험 상황에서도 더 잘 맞을 수 있는 게 이렇게 좀 뭔가 적절하게 뭔가 샘플을 잘 선택하면은 좋은 상황에서 잘 쓰일 수 있을 것 같다고 해서 흥미로운 예제를 잘 주신 것 같습니다. 네, 감사합니다.
Thank you for all three presenter and also discussion. So I think this is the end of the seminar. 예, 세미나 이렇게 좀 긴 시간에 영어로 이렇게 진행이 됐는데요. 끝까지 참여해 주셔서 감사드리고, 혹시 질문이 있으시면은 유튜브 질문창에다 올려주시면 저희가 정리를 해서 한글로 답변을 드리도록 하겠습니다. 네, 장시간 수고 많으셨습니다. 감사합니다.